Welcome to our online lecture series Radar in Action of the Fraunhofer Institute for High Frequency Physics and Radar Techniques, FHR. What you see here are our headquarters in Wachtberg, in Germany, where nearly 400 experts for high frequency physics and radar technology are working on many different topics. One main topic is the space observation and surveillance with radar. For over 50 years, we have our well-known space observation radar Tyra, which is inside the big white ball about 60 meters high. But in the last 5 years, we are working hard to develop a new space surveillance radar. It was called GSTRA, German Experimental Space Surveillance and Tracking Radar. Half a year ago, the two small, in comparison to Tyra small, containers of GSTRA were still in Wachtberg. But on 1st July, we moved the GSTRA containers to Koblenz, Germany, on a site of the German Armed Forces, where it will go into operation, only 50 kilometers away from Wachtberg, where we are today. Now you see a drone video of the so-called Schmittenhöhe in Koblenz. We are very sorry, it's not live because it's very rainy here today. But you see both containers standing 150 meters apart. On the left side, you see the transceiver container. On the right side, you see the receiver container. The containers have a length of 18 meters, a width and a height of 4 meters, and the radomes have a height of over 5 meters. So, hello again. My name is Jens Fiege, and today in this special edition of Radar in Action, we go inside the receiver container of GSTRA to give you a close look to the radar system and its components. So now I hand over to my colleague, Christoph Reising from the Department Array-Based Radar Imaging, who is already waiting in the receiver container to introduce GESTA to you. Let's go, Christoph.
I am actually in the receive system, and yeah, in the operations room, you see some monitors in the background. And yeah, I first start with the motivation. Why is space surveillance interesting for us? On my first slide, I give you an overview about the distribution of the about 130 million objects in space that are bigger than 1 millimeter in diameter. The source of this is the so-called ESA master model, which gives you an overview and the statistical distribution of the space debris objects. This distribution is based on measurements and beam park experiments. And the state of the numbers I show to you are from February of this year. Now, how are these, what kind of type are these objects you have seen before? The number of objects, as you can see here in this slide, is tendency increasing. You see there are two big steps. I'll show it with the laser pointer here. In the years 2007 and 2009, where first in 2007, the Fengyu satellite was shot down by a missile, and we got about 40,000 new debris particles in space. The second, you see here, the second step is the collision of two satellites with the names Iridium 33 and Cosmos 2251 in the year 2009. And on total, there are about 100K new objects due to this collision. And you can see on the right of this picture, the growth is increasing in the last years. So what about the size of the objects? Here you can see the size of the objects. If you go smaller with the object size, naturally there is an increase in the number of objects, and the critical size where an object will destroy an active satellite is about 1 centimeter in diameter. if you shoot a bullet of 1 centimeter on a solid aluminum plate, you see the result on the right side now. And this is an impact of a 1 centimeter aluminum bullet into a solid metal plate with a velocity of about 6.5 kilometers per second. To get a feeling of what is this velocity about, the collision of Iridium and Cosmos I mentioned before was about 11.7 kilometers per second relative velocity. So what can we do for active satellites to get sure they do not get destroyed by space debris particles? The first hint would be active removal of space debris particles. This is very expensive and complicated, and there are only first missions which plan to do this active removal. Another second part is controlled deorbiting of inactive satellites which are end of life. So yeah, this is done actually for a big number of objects, and it will be mandatory in the future, but this is not law, but only in suggestion. And the last point is to do evasive maneuvers to move some active satellite if a space debris particle crosses and the risk of a collision is too high. For this, you need very precise knowledge of the orbit data, as well as from the space debris objects, as well as of the active satellites. You can say a space surveillance is necessary for future use of space, because otherwise you cannot do such maneuvers, or also the removal is not possible if you do not know exactly where the particles are. So for this getting this good view of the all the particles in space and objects in space, you need to use phase array radars, which are very flexible and can cover big spaces of the space at a very short time. There are some operational systems right now. For example, I will tell you the US has the US Space Surveillance Network, which consists of some sensors. In Spain, there is a system called S3TSR, which is going active at the moment right now. In France, there is the active system called GRAPHS, and the ESA has one system called ESSAS. The Fraunhofer FHR built the receive system for this system of the ESA, and it's operational now in Spain. Now we get a first look about the facts about the GSTRA system. GSTRA is also a phased array system. It's operating in L-band at around 1.3 gigahertz. It's built for surveillance of low Earth orbit. The maximum height of the objects, which you can see is 3,000 kilometers. You can steer mechanical and electronic way the beams. There are various operation modes called search modes. There are 4 different search modes. There is a so-called tracking mode with a prior knowledge of the particles, and a mode called track while scan mode. All product assurance of the GSTAR system is based on ECSS standards. The system itself is partly mobile and will be remote controlled by the German Space Situational Awareness Command in Uden. So now we have the chance to get an inside look into the system, and I will show you what you can find inside the system. At the entrance of the technics room, you see here some air conditioning systems, one system for compressed air on the left side, additional air conditioning on the whole right side of the room, and last but not least, here is a very big computer system which is very high performance. The performance is more than 500 teraflops, which was when we built up the system, one of the I think almost the 500 top systems in the world. On the right side, additional air conditioning, the positioning system, which has the control here, and all the radar capabilities are mainly inside of this cabinet. You have here system control system, a waveform generation, signal distribution. The whole digital beamforming unit is located here, some power supplies, and all network stuff necessary. So next, I will give you an overview about the antenna front end, and I'll have to move to the antenna for that. So now I am in the antenna front end. You can see here a 265 active element, and which are always, every element has a cavity backstack patch antenna for the transmission and the receive. Here we are in the receive system, but the antenna front end is exactly the same. At the outer part of the circle, there are additional dummy elements for coupling issues. And yeah, I will go to the back side of the antenna to show you the back end as well. So now you can take a look into the back end of the antenna. On the outer part, here you can see the power supplies, distribution of signals, and everything else. And the main part of the antenna you see here are the so-called plank structures. There are a lot of them. All are connected via fiber optics for high-speed data transfer. Yeah. You see, at the moment, there is one plank missing. And that is because we, especially for this talk, we got one plank unit here and removed the top cover. So you can see inside there are 3 channels. There are also planks with 4 channels included. The first stage of the digital beamforming is done here, and then sent all to the cabinet I showed you before. You can see here the complete interior. In totally, the antenna has 264 receive channels. Yeah, and that's it. I hope you got a short view into the interior of the system, and I will go back to my presentation now. While I'm doing that, my colleague is moving the antenna so you can get a look and feel about how it looks when the antenna is moving. Because we are now, the scissors lift we are on is now in the bottom position. We can just move our polarization, and azimuth and elevation cannot be moved at this time. Yeah. In general, it is possible to steer mechanical in all 3 axes. So I'll move down and yeah. Yeah, now we are back here on the presentation screen. Okay. My colleague told me at the moment you are seeing the moving of the antenna frame. I hope this will give you a good experience. I show you some key features about the system which are special for the system. First, I mentioned before the digital beamforming. On the left-hand side, you can see one pencil beam. This is the standard case of the most radar systems, where you can see there is one point with maximum gain here in the middle. And this is what the most radar systems do. In the GSRA system, we are possible to do many different beams here. You see 5 beams here now, but this is only the first operation mode. In principle, you can build up to build many beams, and GSRA is a complete software-defined radar. Some key facts about the performance of the system. As I mentioned before, 256 elements in RX and TX are here. You have a very low system noise figure with less than 1.5 decibel, including the analog digital converter, a very high transmit power with more than 1 kilowatt per element. And yeah, you see the other key facts. Now there is some notes about the scan strategy for the surveillance or search modes. You see the 3 fences for mode 1, 2, and 3 on the right side. The entire field of view, you see all beam positions are scanned permanently. You can shift these beam positions within milliseconds and yeah, and see everything. The number of integrated pulses differs by the direction where we are looking at, because for the more external beams, we have less antenna gain. And yeah, at the same time, we have to cover more range because of the off-broadside angle is bigger and the ranges increase by this angle. On the bottom left, I can show you there is one particle which crosses the beam vertically. We make sure this will be detected also because we have the 2-row fence with which is in a triangular arrangement. The other 2 modes are the mode tracking, where you give a 2-line element set to the system. This is a format for orbital data of space objects. And when you give this TLA set to the system, there is a short capture period, and GSRA calculates the future orbit positions and tracks the object all the time. In mode 7, there is basically a search mode. And when GSRA detects a particle multiple times, it generates an additional beam. So you can follow this, as you see in the picture on the bottom right. So I give a short lookout about the space surveillance in Germany. We are planning to use networks of radar systems. At the moment, we have built up the first system, GSRA, and we are planning to build a second receiver. And yeah, for some simulation data, you see here three objects, three systems which consist of transmit and receive system each. And yeah, this is only an example configuration. About the performance of detection, you have on the left side, there are 3 systems which each operating in a monostatic way. On the right side, you see the if you fuse this data and yeah, do some data fusion techniques to increase to decrease the number of the to decrease the size of the detected objects. You can see the minimum detection, the minimum detectable size you get here is on a bigger range on the right side. And between the sensors, the RCS decreases significantly, so you can detect much smaller objects. Another performance lookout would be for orbit determination. There are 3 steps on the on this slide. On the left, you have one monostatic system, and yeah, all of the black dots is a propagation 90 minutes into the future after the first detection of the object. In the middle, you see the fusion of the data only if you know the detections of the systems, and the systems itself do not know anything about the other ones. And the right picture finally shows if you use all multistatic aspect angles and signal paths and fuse all the on-row database, and you gain a reduction of the root mean square error by a factor of 8. So to conclude, there are some main facts. The space surveillance of the LEO is absolutely essential for future use of space. GESTRA is a good addition to the German capabilities, and the future use of GESTRA systems in radar networks can enhance performance. Concluding, you can say without future research, the use of space will not be possible in the future. So thank you for your attention, and I'm open for questions now.
Thank you, Christoph, for your nice presentation. And there are some questions. The first question is, what is the diameter of the antenna?
The diameter of antenna is about 2.8 meters.
The next question is, what is the array gain in dBi?
The array gain in dBi for the pencil beam case is short about, I'm not quite sure, I think it's 30.9 or 30.8 dBi.
Okay. The next question, if your antenna is circular polarized, then what is the benefit to rotate the antenna on axis?
There are various operation modes, as I told you before. One mode is only linear polarization, and for this, you get effects with Faraday rotation or other ionospheric effects, and you can compensate this by the mechanical polarization. There are also modes which are working in both polarizations and can create a circular polarization. But there's lots of math and post-processing for this. So if you know and if you have the chance to compensate the polarization errors before, it's a nice to have.
Oh, very good. So how many digital receivers are available and what is the effective throughput?
There are 265 elements, and every element has a single digital receiver which can work in both polarizations. I don't get the question for throughput. If you mean data rate, then this is based on how many beams are used simultaneously, and can differ in the practical use.
Okay, I think that was the question. So the next question is more general. Can you see non-metallic objects?
Can we see non-metallic objects? We are using basically the design is for metallic objects, but as far as you know, there is also a reflection of non-metallic object, but the performance is not as good as with metallic objects.
Okay, and here are the next questions. Is the performance of the system affected by the ionosphere, in particular by such parameters as the total electron content and the turbulence level?
Yes, the system is, and I think every radar system is, because of the behavior of the electromagnetic radiation. Is an aspect for every radar system which is looking to space, and it varies with the sun activity and other facts about space weather.
Okay, so many questions today. Are there already talks concrete plans to bring Gstra-like antennas to other places in Europe?
That's not my decision. I heard there are some interested partners, but I cannot decide if we are bringing the system there and under what conditions.
Okay, but we are hoping that. What is the reason for the separation of the two containers roughly 100 meters away? Why not nearby?
It's simply because of decoupling. If you send with the transmitter, if you transmit some energy, the receiver will totally get in saturation, and to prevent for errors, they are separated by about 100 meters, which is basically a minimum.
Why do you choose L-band versus higher frequencies such as S-band?
There are many reasons. One first reason is if you are on a low frequency, it's basically almost most time it is cheaper to build up high power transmitters. Another one is the loss is not very high in L-band. There is a null at this point where it's a local minimum, and so the choose goes for L-band. There are other countries which are operating in S-band as well, I know, and yeah, always is a compromise.
We have a question from India. They build up a center of excellence in India, and how can we work with you in realizing the same? So I would say please contact us via email, and then we can discuss it in detail.
Exactly. Send an email, and I will give this information to the people who are working on corporations and such things, and we should get in touch.
What are the range, Doppler, and angle resolution in scan mode and in tracking mode?
The range, Doppler, and angular are based. I cannot give you the exact values because I'm not allowed to. But I can say from other publications you can get bandwidth data and such things. I think you can get a very good feeling if you are looking at the key facts I gave to you and other people of us gave to us. We have a very performance system compared to other systems which are operational right now.
Okay. What kind of pulse waveforms does Gstra transmit, and what are the benefits of using those waveforms in comparison to FMCW?
Very interesting question. In principle, Gstra can transmit various different waveforms. For the first steps, we are using some COSTAS-based codes. One advantage is the very good ambiguity function in Doppler. You can always discuss what are the benefits of FMCW and pulse radar. We choose to build a pulsed radar system, basically I think it's for decoupling of the transmitter and receiver.
Okay, we have many questions today, but here we have now, the time is nearly over, so here's the last question. Are there other comparable phased array radar systems in other European countries, and it is possible technical to collaborate by using foreign antennas as receivers?
In principle, you have to choose the same transmit-receive band in L-band. As I said to you before, we are around 1.3 gigahertz. There are other systems in L-band. In Germany, we can cooperate, especially with our Great Tyra system. I think Jens has told you about it before. We can cooperate with, basically with the radio astronomy station in Effelsberg, which is nearby, about cooperations to other European countries. I don't know exactly what they are planning in this cooperation mode, and we are only the supplier of the system and the builder of the system, and the operation will be, as I said before, from the German Space Situational Awareness Center. So if you're interested in cooperation, send a contact mail to us, and we will hand them over to the colleagues in Uden.
Okay, thank you again, Christoph. Thank you all again. Thank you for your questions and certainly for your participation. If you have further questions, you can contact me. Now, if you have some noise, we are here nearby a military base. Nothing that happened, it is only training. So now I will inform you about the next events next week. We have next week this German event. Here are the next English events. In 2 weeks is quality control in production with radar-based surface imaging, and the other you see. If you have interest, please visit our website and register on this page. Here are the contact dates. If you have any further question, contact me or contact Christoph Reising. And I hope we see us again here at Radar in Action. Goodbye from Germany.